Hey guys, today we're going to be going one step further in solution stoichiometry. We're going to be looking specifically at a technique called a titration, and within titration we're going to be looking specifically at acid-base titrations. So you can use titrations for a couple of different things, but today we're going to be looking specifically at problems that assess acid-base neutralization reactions and how we use titrations to solve for unknown concentrations within that. So let's go ahead and get started by doing some practice problems, and then I'll give you guys a chance to practice on your own. So as with a lot of the different types of problems that we've seen in solution stoichiometry, when we're doing acid-base neutralization reactions, you're oftentimes going to be given a unit such as grams or moles, and you're going to have to convert it into molarity in some way, shape, or form. Although sometimes you're going to be given molarity and convert it out into grams or moles. For instance, if you were to have to figure out how many grams or moles of an acid do you need in order to react with a certain amount of base, or vice versa, it's really important to be able to do the nuts and bolts of solution stoichiometry well before we approach this technique. If you need to go back and rewatch any of the prior videos about solution stoichiometry and how to perform basic solution stoichiometry problems, you should go ahead and do that now and then continue with this video a little bit later. So as I said in the introduction, a titration is a very specific technique that we use in chemistry to determine the molarity of something that we don't know the molarity of. Now, to do a titration problem, you're going to need to know the molarity and the volume of one of your substances in order to be able to find the molarity of your unknown. So, for instance, if we were to have an acid that we don't know the molarity of, you need to know the volume of the acid you have, plus the molarity and volume of the base that you add in order to neutralize that acid. So, titrations require some very specific things. The first thing that a titration requires are tools such as a burette, which is our most precise volumetric measuring tool that can measure at a range of volumes. We also will need a Erlenmeyer flask to be able to contain the actual reaction itself. And finally, you're going to need a known concentration base. So for instance, if I know I have 1 molar sodium hydroxide, I'm going to be able to do the problem. If I don't know the molarity of the base, that's going to be an Now, one of the most important things about titrations is the use of an indicator. An indicator is a chemical that changes color at a given pH. In this case, when we're using an indicator, we're looking to find what is called the equivalence point. Now, the equivalence point is where you've exactly met equal number of moles of acid and base. Now, we're going to talk a little bit more about equivalence points later on in the year when we get to acid-base equilibrium, but for now what you need to understand is that a titration is going to end at the equivalence point for these purposes, neutralization reactions, but the titration will not always end at the equivalence point. So you want to make sure that you understand that the equivalence point is where we're ending for these titrations. That is where the color change will need to be. But that's not always the case. Sometimes the end point, or where you stop the titration, is going to be different than the equivalence point. But again, we'll talk about those specific types of contexts later on in the year. So the math within a titration problem is actually fairly straightforward. Specifically within acids and bases, any titration problem is going to boil down to solution stoichiometry. In acids and bases, you first have to assess whether they're monoprotic and monohydroxic, or say diprotic and dihydroxic. What that means, if it's monoprotic, it has only 1 acidic hydrogen. If it's diprotic, it has 2 acidic hydrogens. Now, at this point of the year, you're going to be told whether an acid is monoprotic or diprotic, but later on in the year, you're going to need to know the difference between them. The other thing is monohydroxic or dihydroxic. So monohydroxic means that the actual base has only 1 hydroxide polyatomic ion, whereas dihydroxic means it has 2. Now in this context, we have used for dilutions before molarity of the first times volume of the first is equal to molarity of the second times volume of the second. In titration problems with acids and bases, the reaction that's actually going on is 1 hydrogen ion is reacting with 1 hydroxide ion. So a more succinct way to do the math in titrations is to say the molarity of hydroxide or the molarity of hydronium. So it would be molarity of H plus ions times the volume of your acid is equal to the molarity of hydroxide ions times the molarity times the volume of your base. Okay? That way you're sure that if it's a monoprotic or diprotic, you've accounted for the extra hydrogen in any of the diprotic or dihydroxic compounds. One thing to be aware of when we're doing a titration problem, beyond just the simple math that's needed to solve for the unknown concentration, is what are we actually looking at as we're doing a titration. Now, a titration problem is effectively just a limiting reactant problem. And at our equivalence point, we no longer have any limiting reactant. At the equivalence point, the number of moles of H plus and the number of moles of OH minus are exactly equal. So no one's the limiting reactant anymore. What we can actually do is we can put this onto a graph. Now the graph that we're going to see in terms of this titration is going to be on the x-axis, the number of moles or number of milliliters of base added. Normally you're going to see that as volume because that's actually the data we're collecting. On the y-axis you're going to see pH. Now for our purposes today, the only thing you need to be able to do is identify the equivalence point. In acid-base equilibrium, we're going to actually start talking about how you identify the pH at any given point of a titration, but you don't need to be able to do that yet. The other thing to be aware of is that with any titration problem, it doesn't actually matter if you're adding the strong base to a weak acid or a strong acid, because the equivalence point will be at the exact same number of milliliters of strong base added. So if you look at the graph, you can see that I've circled the equivalence point. Now, the equivalence point is not always at the same pH, but again, we're going to be talking about that a little bit more when we get to acid-base equilibrium, but you don't need to bother yourself with that now. The key is the equivalence point is right where you go from an upward-facing graph to a downward-facing graph. We call this the inflection point. So let's do a practice problem. In this first practice problem, what we're going to see here is that we're combining sodium hydroxide, which is a monohydroxic base, and hydrochloric acid, which is a monoprotic acid. This means stoichiometrically the H plus and OH minus are in 1-to-1 ratios. We have, in this situation, 0.5 molar sodium hydroxide, and we know that in order to reach the equivalence point, it took 25 milliliters, or 0.025 liters, to get there. For the acid, we know that we started with 50 milliliters of the acid, so 0.050 liters. In order to solve for the molarity of the acid, we're going to set up our equation. Molarity of the hydroxide times the volume of the base is equal to molarity of the acid, or H plus, times the volume of the acid. We solve for our unknown, which is the molarity of the acid, and what we're going to end up with is that the concentration of the H plus, or the concentration in this case of the HCl, is 0.25 molar. So we did this problem. It's basically a proportional problem, so you're setting it up just like you would. You could also set this up like we used to do with dimensional analysis. That's fine too. Doesn't actually matter how you set it up, but in the end, you get to the unknown, which in this case was the concentration of our acid. All right, so this next practice problem is going to be somewhat of a challenge. But given the skills you already know from the rest of the unit, you should be able to do it. Take a look at this practice problem, pause the video, take a few minutes to solve. If you get stuck or if you get an answer, go ahead and unpause the video, come back, and we'll work through it together. Okay, now you've had a couple of minutes to solve, let's work through it together. Now, seeing as this is a standard neutralization problem, we can approach it as such, but it looks a little different than anything we've seen before. In this case, we're given the mass of a diprotic acid and the amount of a monohydroxic strong base it took to fully neutralize that acid. So let's initially set up our molarity of H plus times volume of the acid equals molarity of OH minus times volume of the base, and we'll look at how it works. Now, because we're dealing with a diprotic acid, for every 1 mole of acid, there's 2 moles of H plus. That means that when we're actually doing our neutralization, it takes 2 hydroxides to react with every 1 mole of acid. All right, so this is very important to understand that we're going to have to figure out how to solve for this in the end using the understanding that we have a diprotic or dihydroxic. So we're going to solve for this in a few minutes. The first thing we're going to do is figure out how to use grams. Now, here we have molarity times volume. Molarity, which is in moles per liter, volume, which is in liters. Multiplying the two together gives us simply moles, moles of H plus in this case. So what we really have here is the moles of H plus are equal to the molarity of OH minus times the volume of the base. Now, if we know this, then what we can solve for is the number of moles of H plus present. Which means that we have 0.0037 moles of H plus. Now remember, it took 1 mole of our diprotic acid to provide 2 moles of our H plus, which means we need to divide this by 2 to figure out how many moles of acid we started with. So we're going to take this number and divide it by 2, which means we actually have 0.00185 moles of our acid. Remember, this is because it's a diprotic acid. You wouldn't do this with a monoprotic acid because for every 1 mole of a monoprotic acid, you only get 1 mole of H plus. In this case, it took 0.00185 moles of our acid to provide 0.0037 moles of our H plus. That's the moles. We also have grams. Remember, molar mass is grams per mole. So we have grams, we have moles, we just have to do the quick math to solve for molar mass. So what we're going to do is we're going to take our number of grams and divide it by our number of moles. We solve. And don't forget sig figs here, all right? We have 4 sig figs throughout. So we need 4 sig figs in our answer, so it's 267.8. Now, make sure you go through this problem again if you had any questions of how it was done, all right? But there's our answer. That wraps up today's video. Let's do a quick recap. We started by talking about what is a titration. We looked at the technique involved in a titration. And then we looked at the math involved in solving acid-base titration problems. Now, in the next video, we're going to be talking about a different type of titration, but the technique is largely the same. I would like to thank those who wrote, filmed, and edited this video, Lindsay Schissel and Vivian Tran. I'd like to thank you guys for watching it, and I'll see you in the next one.